And especially recently, this metric has been hotly debated in the social media. The reason is that a number of open source models came up on the leaderboard and started challenging the incumbent GPT-4 and GPT 3.5. And this put in question the like how valuable this benchmark is. And I think it's worth really digging into the ins and outs of HumanEval and understanding how it works. And this will allow us to really interpret the results of this benchmark. But before we get there, let's look at the GPT-4 metaphor. So HumanEval is the online coding test of the language model universe. And just as coding test screens candidates for their real-world coding skills, offering a practical glimpse into their problem-solving abilities, HumanEval tests language models on human-generated tasks to see how well they perform on real-world challenges beyond abstract benchmarks or theoretical capabilities. So this benchmark was developed by a team at OpenAI. It was first published in the Codex paper, which had a title Evaluating Large Language Model Trained on Code. The task that is supported by this benchmark is generating standalone Python functions from docstrings. And the name may be a little bit confusing. It's called HumanEval because the data set and associated unit tests were handwritten by people, but the evaluation is actually automated. And it's automated through these unit tests that are written to test the performance on each of the problems within the data set. So the metric here is called PASET-K, and we'll dig a little bit deeper into this metric in a bit. But first, let's look at some examples from this data set. Starting with a simple example, the function is called increment list, and we have the docstring which says return list with elements incremented by 1. It's rather simple. The thing you can see underlined here or highlighted is actually a completion from a language model. And in this case, it's rather straightforward. But then there are some more complex examples. So the next one up requests the language model that given a non-empty list of integers, return the sum of all of the odd elements that are in even positions. So again, a little bit more complex. And this goes further. So in this case, we get a function to encode a string by cycling groups of 3 characters. And we request a model to write the decode function for this specific encoding. And as you can see here, like it actually requires some programming skills that many people might not necessarily have. So it could be a challenging task for a language model. The metric, which is PASET-K, is defined in a way that we generate K code samples. So most often right now we use PASET-1, which means we generate a single code sample and we check if the problem is solved with the sample. But historically, it was often the case that we would generate, we would evaluate PASET-5 or PASET-100 and maybe generate 100 different code samples and then check if at least one of those generations solves and passes our unit tests. And then we report the total fraction of problems that is solved by our generations. Now, it's important to note that even if we report PASET-1, it does not necessarily mean that we generate only one example, because this can lead to high variance. Instead, what is explained in this paper, and I think what is also done during the evaluation, is we generate a higher number of code samples. For example, for PASET-100, the team would generate 200 samples, and then we would count the number of correct samples within this bigger group, and then calculate an unbiased estimator. So we don't need to dig into this metric. We don't need to necessarily understand this now, but it's important to note that calculating PASET-5 may require you actually to do like 20 generations. There are some tricks that were involved in running a HumanEval. For example, even if you are calculating PASET-1, you may actually generate more samples. And the important thing is you pick one for evaluation before checking the score. And this can be seen kind of like a beam search. You can generate multiple samples and then pick the one that you feel is most probable of being the correct one. And the team checked a number of heuristics. The one that seemed to work best is to pick the sample with the highest mean log probability. You can also experiment with different ways of decoding from the model. When generating from the model, you can adjust the temperature. And here the temperature can be different depending on what is the K in our metric. So if we have like a single sample we want to generate, then it makes sense to do it with low temperature, like 0.2. But if we try to evaluate against pass at 100, then maybe doing this with higher temperature to get more diverse examples and counting that at least one of them works is a better strategy. So again, this temperature is a function of the K in our metric. And the generation is not greedy decoding in the paper. They actually did nucleus sampling with top P at 0.95. I encourage you to check out our course on building LLM applications, where we get into more details of different sampling methods. In the case of the original HumanEval, there were no specific prompt design tricks, I believe, but in some subsequent work that actually scores high on the benchmark, you can see some prompt engineering being applied. I think the model or the application that is high at the top of HumanEval, at least on papers with code, is Reflection, which applies some of the prompt engineering tricks to get a really high score. So a side note here, historically, code generation was often evaluated with BLEU metric. This is a metric that dates back to 2002. The original use case was for machine translation. The key idea of BLEU was to check how close a translation is to a reference translation written by a human expert. And then to measure how well a candidate translation performs, we compare it to a set of references. We calculate the percentage of n-gram overlaps, and this gives us the BLEU metric. Historically, it performed really well for machine translation. It allowed to progress the field, but when evaluated on code by the team, it seemed like it did not work at all. So using BLEU metric, it was very hard to distinguish the correct generations from incorrect generations. And for this reason, I think this unit testing was a really smart idea, where you can evaluate the code generation in an automated way, in a way that is meaningful, that checks whether the problem actually was solved, and gives some creative liberty to a language model of coming up with their own way of solving a problem. So that gives us like some progress over the historic metrics like BLEU. So to summarize, HumanEval, on the positive side, it measures meaningful skills. I'd like my language model to be good at generating code. It allows for automated evaluation of language models. It mitigates some of the problems associated with the older approaches, such as the BLEU metric. On the negative side, it is pretty small. There are just 164 examples in the dataset, so this makes it prone to overfitting. The scope is limited to single Python functions, and it also has the risk of being like contaminated, because the dataset is available on GitHub. So models that there is a risk that newer models might actually be trained on this dataset, and it makes it very hard to benchmark them on the same dataset that they might have seen during training. So hopefully this will help you interpret these results. I think this is from a couple days back, when a new state-of-the-art open source model was published that did pretty well and started to challenge GPT 3.5 and GPT-4 on the benchmarks. And if you really understand how the benchmark works, it's much easier to interpret this leaderboards. I feel it's a pretty good metric, but it should be taken in combination with other evaluations. And I want to highlight some other code evaluation data sets, since we're talking about code. APPS is a much bigger data set that contains also some pretty challenging problems. It's much harder to get a good result on APPS. MBPP is another, I would say, rather simple data set with around 1,000 programming tasks. A good evolution of HumanEval is multiple E, which is a translation of both HumanEval and MBPP to 18 different programming languages. And there's also DS1000, which is a data set based on Stack Overflow questions. So if you want to evaluate code models comprehensively, it makes sense to look at their performance on these different data sets and see which one works best.